A scheduled outage. Technicians enter containment to remove routine boric acid deposits from the reactor pressure vessel head. The work package anticipates standard cleaning, scrape crusts, vacuum residue, confirm acceptable surfaces. Around control rod drive, mechanism nozzle 3, a maintenance worker applies light pressure to an encrusted area with a hand probe. The probe drops inward. Where 150 mm of forged low-alloy steel should resist, there is void. Bore scope imaging confirms what instruments cannot believe: a cavity deep enough that only 4.8 mm of stainless steel cladding, a corrosion liner never designed to bear pressure, separates the hollow from 15.5 megapascals of primary coolant. Inspection halts. The Nuclear Regulatory Commission receives notification within the hour. This single measurement will reshape federal oversight and reveal how years of overlooked signals converged into one of the most serious near misses in American nuclear history. 1st of July, 1977. The Babcock and Wilcox pressurized water reactor at Davis-Besse begins commercial operation on the southern shore of Lake Erie. Early operating logs record coolant temperature at 300 degrees Celsius, system pressure at 15.5 megapascals, neutron flux steady across the core. The facility is designed to modern specifications: SA 533 Grade B, low alloy steel for the reactor pressure vessel head, stainless steel cladding on interior surfaces, control rod drive mechanism nozzles attached through J-groove welds. Primary coolant carries approximately 2,000 parts per million boron for reactivity control. The chemistry is stable. The numbers align with design. Within the first operational decade, minor boric acid deposits appear on CRDM housings. The phenomenon is noted but not unusual. Borated water is present throughout the primary system. Small leaks at penetrations are anticipated by design. Industry guidance treats such findings as maintenance items. NRC Information Notice 86-108 addresses boric acid corrosion of carbon steel components. The notice reminds licensees that borated water, under certain conditions, can attack low alloy steel. But the prevailing assumption holds: any nozzle leakage severe enough to cause structural damage will produce visible evidence long before integrity is compromised. By the early 1990s, regulatory consensus and industry analyses agree that extensive reactor pressure vessel head wastage from undetected leakage is unlikely. The reasoning is straightforward. Leaks will be self-revealing. Operators will see boric acid trails. Corrective action will follow. The system is designed with layers of detection: visual inspections, leak rate monitoring, containment instrumentation. In 1988, NRC Generic Letter 88-05 directs plants to implement boric acid corrosion control programs. Davis-Besse commits to monitoring and periodic cleaning. On paper, the mechanism that will nearly destroy the reactor head is explicitly recognized, but it remains classified as a low-probability scenario. The expectation is clear. Detection will occur early. Intervention will be timely. The steel will hold. By the close of 1990, that assumption has already begun to fail. 1990 through 1996. Davis-Besse containment. During refueling outages, inspectors photograph the reactor pressure vessel head. The images show boric acid accumulation, white and yellow crusts clinging to insulation, clustered around several CRDM nozzles. Work orders classify the deposits as routine. Chemistry samples from the primary system show stable pH and dissolved oxygen. Leak rates remain within technical specification limits. The assumption persists: if leakage were significant, containment sump levels would rise. Airborne radiation monitors would alarm, or operators would observe steam or moisture. NRC regional inspectors review the photographic documentation. They note the presence of boric acid, but give greater attention to leak rate trends and radiation field measurements than to the geometry beneath the deposits. Visual inspections follow ASME Section 11 standards. The process is procedural. Observe, document, clean where practical, move forward. Insulation around the head is multi-layered and tightly fitted, restricting direct access to metal surfaces. Full bare metal inspection would require extensive disassembly, a scope judged unnecessary given the absence of alarming data. Later, NRC lessons learned documents will conclude that boric acid deposits at Davis-Besse were not fully removed during at least the past several refueling outages. The crusts were treated as a housekeeping issue. Plant engineers understood boric acid as a chemistry concern, not a structural threat, so long as leak rates stayed within specified limits. Containment sump instrumentation, airborne radiation monitors, and CRDM leak-off lines served as indirect indicators. Outage reports documented cleaning activities with generalized language. Boric acid removed, surfaces cleaned, acceptable condition. What the reports did not state, the mass of residue, the area of exposed steel, or the thickness of material remaining beneath the crusts. The deposits were visible. The procedure was followed. But the underlying corrosion, slow, persistent, hidden beneath porous accumulations, continued unchecked. Inspection programs met the written requirements of generic letter 88-05, yet the very deposits those programs targeted remained in contact with hot steel for years. By 1996, the gap between procedure and reality had widened beyond visibility. 1996 through 2000. Industry operating experience accumulates reports of primary water stress corrosion cracking in control rod drive mechanism. Nozzles at multiple Babcock and Wilcox pressurized water reactors. The cracking mechanism is well understood. Alloy 600 material, high temperature, tensile stress, and exposure to primary coolant chemistry combine to initiate and propagate axial cracks. The Electric Power Research Institute issues guidance on nozzle inspections and susceptibility factors. NRC circulates information notices and technical bulletins. At Davis-Besse, eddy current examinations in 1998 detect minor anomalies around nozzle 3. The indications are reviewed and classified as non-growing or non-safety significant based on available data. Non-destructive examination techniques focus primarily on the nozzle material itself, eddy current testing, ultrasonic evaluation, but not on the surrounding head steel beneath insulation and deposits. The assumption remains, if a nozzle cracks and leaks, the leak will be self-revealing through visible boric acid trails, allowing timely repair before significant head wastage develops. In reality, leakage from cracks at nozzle 3 is largely confined beneath insulation. The borated water does not run freely down the head surface where it would be immediately visible. Instead, it accumulates in a mound of hardened deposits on the downhill side of the nozzle. The leak rate is small, too small to register on global plant instrumentation, but sufficient to sustain continuous chemical attack on the low alloy steel. Temperature at the reactor head approaches 315 degrees Celsius. Borated water evaporates, leaving concentrated boric acid in contact with the steel. During shutdown cooling or transient conditions, the deposits re-wet. The cycle repeats. By the end of 2000, Davis-Besse fits precisely the scenario that earlier industry analyses had acknowledged but assumed would be caught by routine observation. Primary water stress corrosion cracking provides a continuous leak path. The leak is too small for sump-level detection. The deposits conceal the degradation. Non-destructive examinations miss the surrounding head wastage. NRC and industry now recognize the mechanism in theory. The next phase will show how, in practice, the degradation continues undetected. Spring 2000 refueling outage, Davis-Besse Unit 1. Maintenance mechanics enter containment to perform scheduled cleaning of the reactor pressure vessel head. The work package references previous findings, minor boric acid accumulation, standard for Davis-Besse operating history. Removal is categorized as equipment protection and cleanliness. Workers use hand tools, scrapers, wire brushes, vacuum equipment to chip away at the crusts. Photographs taken during the outage show thick, lava-like deposits around several nozzles. The largest mound sits on the downhill side of nozzle 3, appearing in images as a pale, irregular mass adhering to insulation and the head surface. The work order directs partial removal. Crews scrape accessible areas. Vacuum hoses collect loose material. Condition reports document the boric acid and note corrective actions taken. NRC inspection summaries reference the recurring deposits, but accept the licensee's response as adequate. No comprehensive bare metal visual examination follows the cleaning. Insulation is not fully removed. The geometry around each nozzle annulus is not directly inspected. Post-event analysis will show that corrosion was already well advanced under the deposits, with wastage progressing beyond superficial pitting into deep sectional loss of the low-alloy head steel. Metallurgical back calculations suggest that a substantial fraction of the final cavity volume, ultimately measured at approximately 2,050 cubic centimeters, likely existed, at least in part, by the time the 2000 outage concluded. The work scope reduces the visible mass of boric acid, but does not expose the underlying damage. Temperature, pressure, and leak rate data remain within normal ranges. Chemistry logs show stable boron concentration. Containment radiation monitors register background levels. Every measured parameter suggests routine operation. Incomplete removal allows the corrosive process to continue between outages. The deposits reform. The steel continues to dissolve. The cavity deepens. By the close of the 2000 refueling outage, Davis-Besse appears to inspectors and operators as a plant in compliance with its monitoring commitments. Beneath the insulation, the reactor pressure vessel head is failing. Mid to late 2001, NRC headquarters, Washington, D.C. Staff analysts evaluate whether to require immediate shutdown of a group of pressurized water reactors with similar design and operating histories to inspect for CRDM nozzle cracking and possible head corrosion. Probabilistic risk assessment models estimate the likelihood of nozzle failure at Davis-Besse. The calculations indicate that risk exceeds typical agency acceptance guidelines. The technical case for shutdown is documented. First Energy, the plant's operator, submits arguments for continued operation until the already scheduled 16th of February 2002 outage. The utility cites low measured leak rates, prior inspection results, and scheduling constraints. Management discussions weigh reliability concerns, information uncertainties, and operational continuity. NRC leadership ultimately grants the request. Davis-Besse continues to operate. Later investigations by the Government Accountability Office and the NRC Office of Inspector General will document the decision-making process. GAO Report 04-415 states, NRC should have, but did not identify or prevent the corrosion at Davis-Besse because its oversight did not generate accurate information on plant conditions. The GAO review finds that even NRC's underestimated risk calculation exceeded levels the agency generally accepted as reasonable. Yet the E-Curry plant ran for several additional months. The decision to defer shutdown extends full power operation through a period when corrosion is approaching the stainless steel cladding interface. Borated water from nozzle 3 continues to seep. Deposits continue to concentrate boric acid against hot steel. The cavity continues to grow. Instruments in the control room show no deviation from normal. Containment sump levels remain stable. Airborne radiation readings stay within expected ranges. Leak rate estimates fall comfortably within technical specification allowances. Probabilistic risk models indicated shutdown was warranted. Operating schedules and information gaps influenced the final decision. The mathematical models were correct. The degradation was real. But without direct physical evidence, without opening the insulation and inspecting bare metal, the corrosion remained invisible. By late 2001, the reactor pressure vessel head at Davis-Besse had months, perhaps only weeks, of structural integrity remaining. 1998 through 2002, Davis-Besse reactor pressure vessel head region. In the years following the discovery, laboratories reconstruct the conditions that created the cavity. Structural assessments and chemical analyses attempt to reproduce the environment beneath the boric acid deposits. The findings are precise and disturbing. Operating crews had believed that head surfaces near 600 degrees Fahrenheit, approximately 315 degrees Celsius, would remain largely dry, limiting boric acid corrosivity. The assumption was logical. High temperature promotes evaporation. Borated water should flash to steam, leaving only trace residue. In practice, the combination of small, continuous leaks and insulation geometry produced a wet, dry, cyclic environment. Borated water seeped from cracks in nozzle 3 and its J-groove weld. The water contacted hot steel and began to evaporate. As water boiled off, boron concentration increased dramatically. Localized boric acid solutions became far more aggressive than the dilute coolant in the primary system. During shutdowns or coolant transients, the deposits re-wetted. The cycle repeated: concentration, evaporation, re-wetting, each iteration driving corrosion deeper into the low alloy steel. Measured and estimated corrosion rates range from 5 to 7 millimeters per year. At those rates, the cavity observed in 2002 represents several years of continuous attack. The entire carbon steel portion of the head in the wastage zone was eliminated. Only the stainless steel cladding remained. NRC Bulletin 2002-01 documents the condition. The minimum remaining thickness in the affected area was found to be approximately 3/8 inch. This thickness was attributed to the stainless steel cladding. The cladding, never intended to serve as a structural pressure boundary, was the sole barrier between the reactor, coolant system at 15.5 megapascals and the containment atmosphere. Localized environment beneath the deposits behaved completely differently from the hot and dry assumption used in general corrosion assessments. The head was effectively exposed to concentrated boric acid for extended periods. Calculations show that by early 2002, the reactor coolant pressure boundary in the affected region consisted only of a thin layer of stainless steel, carrying stresses it was never designed to bear. Late 1990s through early 2002. Davis-Besse control room and containment monitoring systems. Control room operators review daily logs, reactor power, coolant temperature and pressure, leak rate estimates, containment radiation levels. Every parameter trends within technical specification limits. Containment air particulate monitors register background activity. Sump level sensors show normal accumulation. Gaseous radiation monitors detect no anomalies. Reactor coolant system instrumentation is designed to identify loss of coolant accidents and significant leakage events. The expectation is clear. Any substantial breach of the reactor coolant pressure boundary will produce measurable increases in containment humidity, sump levels, or airborne radioactivity. Surveillance procedures incorporate leak-before-break assumptions, the principle that a growing crack will leak detectably before it ruptures catastrophically. In reality, borated water seeping from nozzle 3 never reaches sump instrumentation in quantities sufficient to register as a trend. The leak evaporates on the hot head surface and within the multi-layered insulation region. Water vapor disperses into containment atmosphere, indistinguishable from normal moisture sources. The leak rate, likely less than 1 liter per hour, falls well below the sensitivity threshold of global containment monitoring systems. The NRC Augmented Inspection Team report later notes that installed instrumentation was not capable of detecting the type of degradation observed at Davis-Besse. Containment monitoring systems were never designed to detect covered corrosion driven by small, continuous seepage into deposits. The instruments functioned correctly, the readings were accurate, but the readings measured the wrong parameters. Leak rate calculations remained comfortably within allowed limits throughout the final months of operation. Chemistry samples show stable boron concentration and pH. Radiation monitors confirm expected dose rates. Pressure boundary integrity appears unquestioned. Operators and engineers trust the data. The data provides no warning. Technically, Davis-Besse remained within its licensed operating envelope right up to the 16th of February, 2002 shutdown, despite the fact that one region of the reactor pressure vessel head had already lost its entire low alloy steel thickness. The absence of alarming instrumentation reinforced confidence in continued operation. Every monitored safety parameter was green. Beneath the insulation, a cavity the size of a small brick lay hidden. January through 16th of February 2002. Davis-Besse Unit 1. The final weeks of operation proceed without incident. Daily control room logs record steady reactor power, reduced from full output due to fuel cycle burnup, but stable. Coolant temperature holds near 300 degrees Celsius. System pressure remains at 15.5 megapascals. Neutron flux distribution across the core shows expected patterns. Chemistry parameters stay within specification. No significant alarms, no active condition reports concerning head integrity. Senior reactor operators review shift turnover documentation. Auxiliary operators log containment inspections. Maintenance planners prepare work packages for the upcoming refueling outage. The plant approaches its scheduled February shutdown as a routine event. 17 months have passed since NRC staff first evaluated whether to order immediate inspection. The decision to allow continued operation appears validated by the absence of adverse indicators. Retrospective structural assessments conducted months later will show a different reality. By late January 2002, the remaining stainless steel cladding over the nozzle 3 cavity was already carrying stresses near its allowable limits as part of the reactor coolant pressure boundary. Finite element models developed by laboratories such as Oak Ridge National Laboratory analyze the mechanical response of the cladding under differential pressure. The models show margins far smaller than originally assumed for the composite head structure. Cladding thickness, approximately 4.8 millimeters, must resist the full primary system pressure over an area where no backing steel remains. The absence of alarming data reinforces confidence. Engineering judgment based on available information supports the planned outage date, but the engineering judgment relies on measurements that cannot see through insulation and deposits. The decision to wait for the scheduled outage inadvertently allows the corrosion process to reach its most advanced and dangerous stage. On the 15th of February 2002, every monitored parameter suggests a plant operating within its design basis. Reactor coolant leak rate, within limits. Containment radiation, background. Sump level, normal. Chemistry, stable. The control room displays show a facility in full compliance with its operating license. 24 hours later, inspection will reveal that the reactor pressure vessel head has been on the edge of failure. 16th of February 2002, Davis-Besse containment. With the plant in cold shutdown, outage crews begin planned maintenance activities. The boric acid cleanup on the reactor pressure vessel head is a scheduled task, documented in work packages and based on observations from prior outages. Workers anticipate the scope based on previous experience, scrape deposits, collect residues, visually confirm acceptably clean surfaces, proceed to nozzle inspections and other outage work. As crews progressively remove deposits from around control rod drive mechanism nozzles, they work methodically through the head surface. Mechanical scraping, high-pressure water lancing, residue collection into containers. The work is slow, deposits are thick and hardened. Around nozzle 3, the accumulation is particularly heavy. On 7th of March 2002, as a technician applies cleaning tools to the area, the underlying surface gives way. What should be solid forged steel offers no resistance. Visual examination with flashlights and mirrors reveals a void. Initial measurements indicate the cavity is several inches deep and several inches across. Borescope imaging is deployed immediately. The video feed shows an irregular cavity extending deep into the head material. In the deepest areas, only a thin layer of stainless steel remains visible. The low alloy pressure vessel, steel is gone. Inspection halts. Site management is notified. NRC Region 3 receives a phone call. By midday, the information reaches NRC headquarters. An augmented inspection team is assembled. Ultrasonic thickness mapping equipment is brought to the site to quantify the extent of the damage. Measurements confirm the visual assessment. Remaining thickness in the affected area is approximately 3/8 of an inch, the thickness of the stainless steel cladding alone. The cavity volume is later calculated at approximately 2,050 cubic centimeters. More than 150 millimeters of low alloy steel has been consumed by boric acid corrosion in a region covering roughly 150 square millimeters. Only after deposits are fully removed, an action not completed during multiple prior outages, does the true structural condition become visible. Routine outage work, mandated by previous generic communications, has finally exposed what years of operation concealed. March through mid-2002, engineering offices at Davis-Besse, NRC technical centers, and national laboratories. Analysts feed cavity dimensions, material properties, and operating conditions into structural models. The objective is to determine how close the system came to failure. Stainless steel cladding is designed as a corrosion-resistant liner, not as a standalone structural component. Its mechanical properties and thickness were never intended to serve as the primary pressure boundary. Finite element models reconstruct the stress state in the degraded head section. Operating pressure of 15.5 megapascals acts on the thinned region. Cladding thickness of approximately 4.8 millimeters must resist the full differential pressure across an area where backing steel no longer exists. Analyst input material properties: yield, strength ultimate tensile strength, fracture toughness. Temperature conditions are incorporated, approximately 300 degrees Celsius at the head surface. Results show stress levels approaching or exceeding conservative design assumptions for the cladding layer alone. Cyclic loading from heat-up and cool-down transients adds fatigue considerations. Pressure transients during normal operation, startups, shutdowns, load changes, impose additional stress cycles. The models assess potential failure modes, ductile rupture of the cladding, propagation of a through-wall crack, and the consequent initiation of a small break loss of coolant accident. Engineers consider scenarios. If the cladding had failed during operation, primary coolant would have discharged into the gap between the head and insulation. Depending on breach size, leak rate could have escalated from undetectable to significant within minutes. Nozzle ejection, a scenario in which differential pressure expels a CRDM nozzle from its penetration, becomes plausible if cladding rupture compromises the structural connection. A small break loca in the confined geometry of the head region presents challenges for isolation and mitigation. NRC lessons learned reports describe the Davis-Besse event as one of the most significant near misses in the history of US nuclear power. Post-event probability analyses indicate that the risk from Davis-Besse's degraded head exceeded levels NRC typically considered acceptable for continued operation, even before the damage was discovered. Engineering quantification transforms a visual anomaly into a risk benchmark. Failure margin was extremely small. Exact hours or days to potential rupture remain uncertain, but the consensus is unambiguous. The plant was very close to a serious event. March through December 2002. NRC Headquarters, Davis-Besse. Within days of the cavity discovery, NRC forms an augmented inspection team to investigate the circumstances and root causes. A lessons learned task force is established to evaluate regulatory oversight processes. Davis-Besse enters an extended shutdown overseen under Manual Chapter 0350 procedures, a framework reserved for plants with significant performance deficiencies. The findings are documented across multiple reports. The AIT report details the physical condition, inspection history, and immediate technical issues. The Lessons Learned Task Force examines how existing oversight processes, generic communications, and inspection programs failed to prevent such severe degradation. The Office of Inspector General conducts an independent review of NRC decision-making, particularly the choice to allow continued operation into 2002. GEO Report 04-415 concludes, NRC should have but did not identify or prevent the corrosion at Davis-Besse because its oversight did not generate accurate information on plant conditions. The review identifies gaps in how NRC integrated probabilistic risk insights, operating experience, and plant-specific inspection findings. The decision to defer shutdown is scrutinized. Retrospective analysis shows the plant operated months longer than conservative safety margins would have permitted had the true head condition been known. First Energy faces significant regulatory consequences. NRC issues a civil penalty of $5.45 million, one of the largest in agency history at the time. The penalty reflects findings of multiple violations: failure to adequately implement the boric acid corrosion control program, inadequate corrective actions for recurring deposits, and failure to ensure that inspections provided reliable information about pressure boundary integrity. Corrective actions are extensive. The entire reactor pressure vessel head must be replaced. All CRDM nozzles undergo comprehensive non-destructive examination. Safety culture is reviewed. Root cause evaluations examine organizational factors, oversight processes, and decision-making practices. Independent verification and validation precede restart authorization. Davis-Besse remains offline for more than 2 years. The event forces NRC to re-evaluate how it uses risk insights, generic communications, and plant performance data in shutdown and inspection decisions. Regulatory trust erodes. Industry-wide inspection enhancements are mandated. Davis-Besse is no longer just a plant event. By 2004, it has become a federal policy case study in oversight effectiveness, cited in GAO and NRC documents as evidence that lessons from prior task forces had not been fully institutionalized. 2003 through 2010. NRC and the United States pressurized water reactor fleet. In the months following the Davis-Besse discovery, NRC issues new requirements and guidance for reactor pressure vessel head inspections and boric acid corrosion control. Previous generic letters and bulletins had been intended to drive effective programs. Davis-Besse demonstrated that compliance on paper did not guarantee early detection. New guidance mandates more extensive bare metal head examinations. Visual inspections must include removal of insulation and deposits to expose actual head surfaces. Routine, non-destructive examination of nozzles becomes standard. Inspection frequencies are tied to plant-specific risk factors: operating temperature, time at temperature, nozzle material, and prior inspection results. Training programs are revised to emphasize the safety implications of boric acid deposits and the importance of complete cleaning and thorough documentation. Inspection methods change. Utilities invest in specialized tooling for head access and examination. Borescope and ultrasonic technologies improve. Industry standards are updated. The emphasis shifts from procedural compliance to actual verification of structural integrity. Operating experience is retained and analyzed over longer. Timescales. Generic communications are cross-referenced against plant-specific conditions more rigorously. GAO and NRC lessons learned recommendations extend beyond technical inspection requirements. Safety culture assessment methods are refined. Shutdown decision processes are re-examined. The integration of probabilistic risk insights with deterministic inspection findings receives increased attention. Regulatory oversight incorporates more direct verification rather than relying on licensee self-assessment. The Davis-Besse case study migrates beyond the nuclear industry. NASA incorporates the event into safety training materials, repurposing it as a cross-industry lesson in near-miss recognition and organizational learning. The agency's safety message emphasizes how technically minor leaks can accumulate into major structural hazards when organizational signals are missed or underestimated. Years later, instructors in nuclear safety workshops open presentations with a slide showing the removed Davis-Besse reactor head. The photograph is now famous, a deep cavity adjacent to nozzle 3, annotated with dimensions and remaining thickness measurements. The image serves as a visual reminder that even well-designed systems require persistent discipline in inspection, maintenance, and integration of diverse warning signs. Fleet-wide changes implemented after Davis-Besse represent the event's most tangible legacy: revised inspection standards, enhanced training, and a recalibrated balance between operational continuity and precautionary shutdown. 2010 to present. Safety courses, regulatory analyses, public records. The Davis-Besse reactor head corrosion event remains a reference case in nuclear safety training and oversight evaluation. The cavity photograph appears in textbooks, conference presentations, and regulatory workshops. Dimensions are cited: approximately 2,050 cubic centimeters of volume, more than 150 millimeters of steel lost in the deepest region, minimum remaining thickness of 3/8 inch attributed to stainless steel cladding alone. The event is studied not for what happened, no release, no dose, no evacuation, but for what nearly happened. US commercial reactors were assumed to have sufficient layers of defense, both technical and organizational, to prevent major degradation of the primary pressure boundary. Davis-Besse revealed that under certain conditions, corrosion could remove essentially all low-alloy steel in part of the reactor head without triggering alarms or being detected by routine inspections. NRC lessons learned. Task force conclusions consistently emphasize the event was preventable. Preventable through more aggressive inspection. Preventable through better integration of risk insights. Preventable through earlier shutdown when probabilistic analyses indicated elevated risk. Preventable through organizational attention to recurring boric acid deposits. The layers of defense existed in design, but implementation gaps allowed the hazard to develop undetected. Davis-Besse demonstrates that nuclear safety depends on conservative assumptions about low-probability scenarios, persistent inspection discipline, and integration of diverse warning signs, from boric acid stains to generic communications and probabilistic risk insights. The event underscores that regulatory oversight and licensee diligence must function together. Instruments provide data. Procedures provide structure. But ultimate safety depends on human judgment, informed by complete and accurate information. The documented story is preserved in thousands of pages: NRC inspection reports, GAO reviews, laboratory analyses, industry evaluations. The reactor head itself, removed and sectioned for examination, became a physical artifact of organizational learning. Metallurgical samples were studied, stress models were refined, training programs incorporated the findings. Davis-Besse did not result in a release, a dose, or an evacuation zone. Its legacy is documentary, a detailed record of how a small, undramatic leak, combined with organizational and oversight gaps, nearly compromised a primary pressure boundary in the United States nuclear fleet. The record remains, the lessons endure.